it all from the homework or anything? Yeah, I know it's straight, it's just equations and you're really asked to calculate field quantities, just doing a couple of mathematical tricks. I want to tell you this though about waveguides, and we will get there. They can be viewed as a transmission line. Now remember with transmission lines, you had to calculate things like standing wave ratio. You had to calculate the length of the wave, well actually for transmission lines, you had a lot of things to do with impedance matching. Do y'all remember that? Stub tuning and things like that. You can think of a waveguide as a transmission line in a sense. It really confines electromagnetic power down a very simple, constant cross-sectional area. And I'll try to get into problems with waveguides later on that are more applicable to the real world, not just abstract stuff. I want to cover a couple of things here today with waveguides. These are things that are important. Let's see here. All right. So I'm going to just sum up for the TE guide what's important. And this is for a TE mode of propagation. And this is a rectangular waveguide. And again, the dimensions are actually, that's not quite what we want to draw. The dimensions of our guide are going to be, the long dimension I'm going to have on a horizontal axis A and B, and then I'm going to say that B is less than A, and it's propagating in the Z direction. Call this X, Y, and assume the propagation is in the Z direction, so this would be the plus Z direction. And that's just a cross-section, it's a piece of pipe, really. And I think everybody understands that. It's a square pipe or rectangular pipe. Now when we have this, the TE mode says that EZ, E in the Z direction is going to be some constant, E naught, and it's times the sine of M pi over A times X times the sine of N pi over B times E to the minus J beta times Z. That's the Z component of the electric field in this direction. From that Z component, we can get all the E field components, the X component, the Y component, and we can get the H field components, HX and HY. And we get those using the curl equations that he has. Now we don't have to do all that. This is the important thing. From there, a few other things that I mentioned before that we found out when we did separation of variables, we came out to this, that the actual beta in the guide, that beta has to do with the actual beta that's associated with the flow of power in the Z direction. Do you follow me on this? Normally they call that K sub Z. Dr. Wentworth just puts it at beta. I like to put this here as K sub Z. So it's the wave number in the Z direction. And what that was equal to, really, if you remember, it was equal to the square root of, and he had beta unguided squared minus, and then there was really going to be the M pi over A squared plus N pi over B squared. If you look at your notes, you'll remember that. Do y'all remember that, class? Now, what I did at that point, I said that's beta in the direction of propagation. It's the Zth component, you might say, K. Then if I take a look at what is the cutoff mode, and that is when the wavelength goes to infinity. Well, since beta is equal to 2 pi over the wavelength, that means beta would go to 0, correct, class? I want to develop this one more time. Do y'all remember this, class? The wavelength in the guide is infinite, literally nothing's propagating, it's just bouncing up and down in the guide. And at that point, now I can say that beta unguided squared plus, or minus actually, minus M pi over A squared plus N pi over B squared equals 0. Then I can take beta unguided squared to the other side, and I can put beta unguided. Actually, I can take this to the other side, and I can say beta unguided squared is really omega squared mu epsilon, and that's equal to the quantity M pi over A squared plus n pi over b squared. Now the only thing I'm doing here is I took the minus this stuff on that side, and then I defined what beta unguided is. It's really omega squared times mu epsilon. Because beta, remember, beta is just omega times square root of mu epsilon if sigma is 0, if it's lossless. Do you all remember that, class? I don't know if you do or not, because some of the stuff, unless you use it frequently, it doesn't stick with you. But does anybody know where that comes from? I'm going to put it way over here. You remember when we talked about the propagation constant, when we developed the wave equation? We found out that the propagation constant was alpha plus j beta, and that's equal to the square root of j omega mu times sigma plus j omega epsilon. Do you all remember that, class? Right? Now if sigma is 0, what happens? If you have sigma 0, then I get the propagation constant simply equal to j beta, right? If sigma is 0, I have j omega times j omega, that's j omega squared. The square root of that is just j omega times square root of mu epsilon. And that means beta is omega times square root of mu epsilon. That's why I'm doing it. To make sure you see it came from the propagation constant, it came from the separation of variables. Well, actually, it came from the development of the wave equation, the Helmholtz equation, the del squared of E. Remember that? Plus beta squared E equals 0 thing. If you don't remember clearly, it was in chapter 6 we did this. So now, listen to me here, because I want to make some points. Here is the cutoff mode. The frequency associated with that is the smallest frequency that will allow propagation down that pipe, down a rectangular waveform. So now what we have to do is find out what it is, and we can see that now we can say omega is equal to 2 pi f is equal to, and then I can go ahead and put down, let me do it up here actually. I want to solve for just omega, and you can put this as omega cutoff here, put it omega c. And then I can put omega c is equal to 2 pi fc, and that's equal to, now I'm just solving for omega here, so I'm going to take the 1 over mu epsilon to this side and take the square root. So I have 1 over the square root of mu epsilon here, and then I have the square root of all that stuff, the m times pi over a squared plus n pi over b squared. I've got all that there. And now I do this. Remember, this is the frequency, the FC I'm looking for. It's the lowest frequency that will allow propagation in the guide. Now I'm going to get rid of the pi's. Do y'all see that pi appears everywhere? Get rid of that too. And then I divide by 2. And so now I see that when I have this equation, I really have n over a squared plus n over b squared, square root of that, times 1 over the square root of mu epsilon divided by 2 is the cutoff frequency. Let me help you with one other thing. This is the cutoff frequency for the MN mode. Now the lowest possible cutoff frequency will be a 1-ohm mode. You don't have a 0 cutoff, all right? And here's why. Look at this equation. What happens when M and N are 0? What is the sign of 0? Sign of 0 is 0. Sign of 0 is 0, right? It can't have a 0 mode cutoff. Do you follow me on this? Nothing will propagate. What is the lowest mode that propagates with the TM, by the way? The TM, this one. This is, oh, I'm sorry, I said T. This is the TM. Oh my gosh, I'm sorry. This is the TM mode. TM mode means HZ equals 0. There is no H field in the Z direction. Everything is transverse. The magnetic field is transverse to the direction of propagation. This is the TM mode, my bad. What is the lowest mode that can propagate? M and N equal 1, right? Anything, if either one is 0, the sign of 0 is 0, so nothing propagates. There would be no EZ, and therefore there would be no other fields, period. So for this one, for TM, write down M equal 1, N equal 1, lowest mode. And for that, a couple other things I'm going to show you. What is 1 over the square root of mu epsilon? Speed of light. Speed of light if it's in air, right, or an air-filled guide. And really that's the velocity of light in an unbounded region that has the parameter mu and epsilon. So I'm just going to call this, I'll just call this V unguided, the velocity of the wave in an unguided media over 2, and then times the square root of m over a squared plus n over b squared. So that, sort of redoing it, that is the cutoff frequency for, and you'll see this is the same thing for TE mode too, but I'm just showing you how it's developed, all right? Now, the way we usually do this, and I'm going to tell you, if you look at this right here, and you see this right here, remember how I got that? I came down and I said beta unguided, or I'm sorry, I said this was the cutoff frequency right here, right? Just watch this. So if I take and divide, or pull out beta unguided squared here, I'm going to go right here and do this. I'm trying not to make it too tough, so I can do this. I can say beta here will be equal to beta unguided times the square root of 1. I took the beta unguided squared, took the square root of, now I pulled it out, all right? And then I have 1 minus, and then it's going to be all this divided by beta unguided squared. What that actually comes down to is simply FC over F squared. And this right here is the one you use. Beta unguided is simply omega times square root of mu epsilon. That's all it is, and that's the mu and epsilon associated with what the waveguide contains, you might say, the inner part of the waveguide. And it's usually air, but it doesn't have to be. It can be filled with a high pressure thing. You can fill it with argon or something if you want a higher, if you want to have high power and you don't want the electric field arcing in there. So you can put a gas in there that has a higher dielectric breakdown strength. But that's beta. And FC has to do with the mode number. The 1, 1 would be the lowest for TM. All right, class? Now, another thing, did I do the velocity in the guide? I don't think I did, but I'll tell you this much, and I'll show you what the velocity in the guide is. If we just take the cross-section of the guide and assume this is the z direction, that's the way it's propagated, here's what's really going on. It's like the superposition of 2 waves that are just ricocheting. Like this. Y'all follow me on that? Now this is going at the speed of light, or if it's air-filled. So the velocity in that direction of energy is less than the speed of light. Does that make sense? Or close to it, right? But it's going to be a little less. However, the phase velocity will be greater than the speed of light. Now phase velocity, remember I told you how it's really kind of an abstract thing that has to do with the intersection of that, the point where that wavefront intersects this surface right here. Y'all remember that? Phase velocity is sort of it's an interesting term, but it is not to be associated directly with energy. Let me show you how to get this. So this is beta right here in a waveguide, right? Now the phase velocity, V phase, is always going to be omega divided by beta. Keep that in mind. That's the definition of phase velocity, and it comes from the argument of a cosine, but I'm not going to do that part yet. So if you look at this, what is this? It's omega divided by beta. Well, beta unguided is omega times square root of mu epsilon, right? Then it's times the square root of 1 minus FC over F squared. Remember, that's phase velocity. Do you all see this, class? This is something that's going to come up again and again. I will ask phase velocity, I will ask velocity of energy, wavelength, things like this. Now, you all see how omega cancels? Everybody? So if omega cancels, now I have this. And really, when you see the 1 over square root of mu epsilon, immediately you think velocity of light. I'm going to do one better. It's really equal to the velocity of light, c over the square root of epsilon relative in the guide. So, and almost always mu relative is equal to 1. I cannot think of a case when you would have a piece of magnetic material in a waveguide. I say that, maybe I can think of a case, but it's a very specialized case at that, and would have to do with filtering. But for now, we're going to assume mu relative is going to be 1. So it's c 3 times 10 to the 8th over the square root of epsilon relative. And then it's equal to the square root of 1 minus fc over f squared. Does everybody see that? Now, look at this for a second. This is the speed of light, right? In a vacuum, if it's c, and if it's divided by the square root of epsilon relative, it's the speed of light in the medium, right? Unbounded medium means the media is everywhere, there's nothing ricochet. But this, if f gets close to fc, f will be above fc, remember that or it can't work. Then this term starts to get smaller than 1, right? And I have 1 over something smaller than 1 means the phase velocity is greater than the velocity of light in an unbounded medium. Do you all see that? And what is the phase velocity approach when f goes to fc? Class? Infinity, right? That means the phase velocity is approaching infinity. And that's what happens at cutoff. Literally, here's what happens. The wave goes from bouncing at an angle to bouncing just up and down, up and down. Nothing propagates, it just bangs back and forth like a resonant cavity. Nothing propagates. Remember, the phase velocity is how fast this point, a constant phase, moves in that direction. And it has no bearing on the velocity of energy. Are you with me? Now, the velocity of energy, write this down. Dr. Whitmer's book does not say this, but the velocity of energy, VE, this is energy. Energy, or speed of, they call it group velocity actually, but group velocity, but it's better called energy velocity, or velocity of energy. This is equal to c over the square root of epsilon relative squared divided by the phase velocity. Now this is the velocity of energy. So if you take c times the square root of epsilon relative squared divided by the phase velocity, you get the velocity of energy. The real equation you may remember from physics is they take the the velocity of energy times the velocity, phase velocity, and they get c squared over epsilon relative. That's the one they use in physics. Group velocity times energy velocity is really the velocity of light squared in that medium, unbounded. You follow me on this? So what that means is because the phase velocity is greater than the speed of light, the velocity of energy is less than the speed of light. By how much? If you look here, what do you see? It's actually equal to c over the square root of epsilon relative. Just take this equation and divide it into that, and it's times, if you look at this, the square root of 1 minus fc over f squared. Do you all see that? So that's how fast energy propagates. And again, the closer you get to the closer you get to fc, the closer you get to speed being nothing. Do you all see that? Now, again, this is with a TM mode waveguide, and I want to tell you one other thing. When you excite a waveguide with a frequency, for instance, we're going to do this. I want to show you this and make sure you catch on to this, because this is important in the real world. Actually, what I should do is show you this with the TE mode, because that's the one everybody uses, practically speaking, for conducting power and stuff, but I'll just show you this in general. So far we're talking about that. This is the TM mode. For the tell you what, I'll do TE and then I'll talk about the modes of propagation, because what you want to do is operate a waveguide in only one mode, so everything propagates at the same velocity. If you have two modes, you have two different velocities of propagation, and if you have a power generator at say 2.4 gigahertz, and you can propagate a mode at 1.2 gigahertz and at 2.4 gigahertz, say you're a little bit above 2.45 gigahertz, both of those modes will be excited. All right, you put in, the way you do this, you put a little thin piece of copper in there, an insert, looks like a short dipole, and it excites the waveguide at these frequencies. And it'll excite both modes, it's like a resonant cavity. And one will propagate faster than the other. What that means is when you try to pull the energy or power out, you have a garbled signal. You have some of the signal moving at one velocity and another moving at another. When you try to get it out of there, if there's any trying to communicate, you can't get anything worthwhile. Do you follow me on this class? You only want one mode. Now, for the TE mode, that was TM. I showed you phase velocity, wavelength on the guide, beta in the guide. I haven't done I did impedance last time, but I'll mention this again, and I'll contrast the two modes. When we have a TE mode, just work with me here. I'm not going to try to make this complicated. Call this the x-axis, this the y-axis. This distance would be A, again, this height would be B. There's a drawing in your book on this, and this is the positive z direction. And the only thing I'm trying to do is show you this is a conducting, think of it like just a square or a rectangular piece of pipe. Good conductors, all right? Now when you have this, for TE transverse electric, it means the electric field is always perpendicular to the direction that energy is being propagated in the z direction. There is no electric field in the z direction. There's only a magnetic field, unlike the last time, right? So now what they'll do in your book, if you can give me the page number on this, I'd appreciate it. I see some of you got your books. Where's the TE mode for the book?
Yeah, it's 394 where it started.
Page 304?
994.
Page what?
394.
394.
Yeah.
All right, now Hz will be equal to some constant, so they call it H naught, some arbitrary value. It's actually the magnitude of the field in the z direction. Then it's going to be times a couple of things. Now, here's how it goes about becoming a cosine. It won't be a sine, it'll be a cosine of m pi over a times x. And then it'll be a cosine of n pi over b times y, and then it'll be e to the minus j beta z. It's going to have the same beta as the TE, but the reason it's cosine is this. And I hate to spend a lot of time on this, but I'm going to show you. When you go ahead, remember the equation we solved before was del squared of e plus beta squared, beta unguided squared, e equals 0. We solved that using separation of variables to get the electric field in the z direction, that component. Do you all remember that class? Now we're going to do the same thing, but we're not going to solve for E. It's going to be actually for H. So now we're going to do del squared of H plus beta unguided squared of H equals 0. I think he does it this way. Does he show a del squared equation in H in the book?
Yeah.
All right, now this del squared right here, we're in rectangular coordinates, so it becomes the second derivative of hz with respect to x squared plus second derivative of hz with respect to y squared plus second derivative of hz with respect to z squared plus beta unguided squared plus, beta unguided squared times hz equals 0. And here, just to bring up the speed here, this is identical to what we did with EZ. We took the three derivatives with respect to EZ with respect to X, Y, and Z, and our three partial derivatives, second order derivatives. Here we do the same thing for HZ. Have to do this. Remember, there's only an H component in the Z direction, right? Then we use separation of variables, so we say we let HZ equal to some function just X of X, some function Y of Y, some function Z of just Z, and then we do these derivative operators. Now this is a little boring and I've done them once before, but I'm going to do them again. You don't have to write them down, just pay attention. So two derivatives on X makes this X double prime times YZ plus, then it would be X Y double prime, right, times Z plus X times Y times Z double prime plus X, Y, Z times beta unguided squared equals 0. You all know what I'm up to, right? It shows it in his book. When I do this, the double prime means two derivatives with respect to X, Y, or Z. Now I divide top and bottom. You all remember my next step? I divide everything by capital X, capital Y, capital Z. Those are the functions of each coordinate. And when I do that, then I get XX prime, X double prime over X, plus y double prime over y plus z double prime over z plus beta unguided squared equals 0, right? And then I make the statement, the only way this can work is if this is a constant, right? And if this is a constant, and if this is a constant, correct, class? And I introduce the constants I use are going to be negative kx squared, so this becomes minus kx squared, minus ky squared, and then minus kz squared plus beta unguided squared equals 0. And here I'm going to say in Dr. Wentworth's book, he just calls this beta. He doesn't call it beta sub z. And he calls this probably beta sub x and beta sub y, I don't remember. So in Wentworth's book, he'll have minus beta x squared minus beta y squared, and then he'll have minus beta squared, that's the actual beta in the z direction. Then we'll have plus beta unguided squared equals 0. It's the same exact thing we did before, correct, class? And now I'll just do this for one of them. Here, if we look at this, this is associated with this, correct, class? So I would say x double prime over x is equal to minus kx squared. I'm going to use kx because it's the one, when you look in other books, most of the time, wave numbers are k, most of the time. And the reason is because you can also write this in terms of a true wave number where it's got direction and magnitude. It would be k bar, and I'll tell you about that some other time, but just understand it's something you'll see in the journals more often, I think. Now when I have this, I'm going to go ahead and bring it down to the level of a differential equation. Now the x double prime, then I'll multiply both sides by x, and I get this, then take this to the other side, and I have x double prime plus kx squared x equals 0. I think everybody sees what I've done, right? Then I'll go ahead and write what that is. That's the second derivative of x with respect to x squared plus kx squared x equals 0, correct? Remember, this is for the magnetic field. This is the one thing that people do have troubles with right here. Now, the solution to that, I'm not even going to bother writing the whole thing, is going to be x is equal to some e to the lambda x. I'm just going to tell you what it is. That's the general formula solution for a homogeneous second order differential equation. Homogeneous means it's set equal to 0, right? You would take two derivatives of this. I'll do it one time, all right? You all remember doing this here? They call that an eigenvalue. You all call that? Take two derivatives of that, so now I get lambda squared times e to the lambda x plus kx squared e to the lambda x is equal to 0, and therefore lambda would be equal to plus or minus kx. Do you all see what I've done there? Right, because if you factor out, you can divide e to the lambda x out of it, and I have lambda squared plus kx squared equals this. And actually what they do normally is this. They'll take it, now it's going to be lambda squared minus kx squared equals 0, and then they'll say that factors as lambda plus kx, lambda minus kx equals 0. So lambda is either plus or minus kx. Do y'all follow me on this? Now, that means actually I need to put plus or minus j in there to make that absolutely true. And then I'll get to the point here. Then the allowable solutions for x would be of the order, that just means proportional to either e to the plus or minus j kx times x, or cosine of kx times x, or sine of kx times x. By the way, does he do this in his book right here when he does the proof of that or not? See, this has to have plus or minus j here, actually, because I'm going to be taking a double derivative that gets rid of that j. right? It makes it what is it? It's a less restricted solution. I don't know the exact words I should use for that mathematically, but there should be a J there. All right. Do you see this solution or not? Does he do anything like this? Well, he does it in one part. I don't know. I think that was in chapter 6. He did that. He showed that. He actually did the differential equation solution. But long story short, this, and this solve that equation. The reason is, you know, when you have something like this, the superposition of these also solves it. So if you have e to the plus jkx times x plus e to the minus jkx times x, that's a solution. Well, that actually is what? That's 2 times the cosine, right? Or it could be e to the plus jx times kx times x minus e to the minus jkx times x. That's equal to what? 2j times the sine of kx times x. Bottom line is, these are just representing various combinations of these. Follow me? Now, that said, now we have to figure out which one of these is actually going to be the one that works, and here's how you do it. When I look at this equation right here, and I say it could be any of these things, and I remember that hz is proportional to x, right? It's proportional to the solution I have to select. Now please understand, this is important. If I have a conducting surface right here, this is the direction of hz. Well, what is the boundary conditions for the magnetic field on a boundary? This is one you didn't cover in Unit 1, I don't think. Normally it's h tan 1 is h tan 2, right? Well, that's absolutely true. Here, h tan 1 doesn't have to be 0. You follow me on this? It does not have to be 0. What actually happens is, at this instant, it has to be a relative maximum. Well, let me just show you what I mean by that. If you have a metal here, and you took a look at the variation of magnetic field intensity, suppose I did it this way. I wanted to plot on this axis magnitude of hz versus z. Well, at this point here, it would have to be either a relative maximum or it would have to be a relative minimum. Do y'all follow me on that? And what I'm trying to do is show you how this is coming in. There is no variation, there's no change here. It means the derivative of hc with respect to the normal is 0. Do you follow me on that? The h field is either a maximum minimum or a maximum positive value, but it is a maximum, which means the derivative with respect to the z-axis, with respect to the normal, which would be either x or y, is 0. Now, think about this. If I choose a sine, the derivative of sine would be a cosine, wouldn't it? But cosine of kx times x, after you took the derivative of that with respect to x, would not be 0 if x was 0. Do you follow me? Therefore, it's the cosine, because the derivative of the cosine will be 0. When you take a derivative of cosine, kx times x, you get what? Minus kx times the sine of kx times x, correct? And when x equals 0, isn't that 0? Class? Sure. It's 0. And that's the reason that this is a cosine and not a sine, and this is a cosine and not a sine. Because the derivative of the h field with respect to the normal direction at a conducting surface has to be a maximum or a minimum. I'm sorry. The h field has to be a maximum or minimum. That means the derivative of the h field tangent to the boundary, hc in this case, has to be 0. And that's an important fact that a lot of people don't know well. And I remember using this very fact on my PhD thesis when I was talking about how to model a boundary of the Earth. My whole PhD was on transients. It was electric field transients related to charge perturbations associated with lightning. It was really about EMP from nuclear weapons, but you can't say it. So when we did that, I had to model the ground, the effect of the ground, and the way you have to do that is this. You basically have to find boundary conditions that work. All right, now, so that is the case for hz, and that's where it comes from, for the TE mode. Now, he has field quantities for the TE mode too. He has a bunch of them. I don't care to put them all down, but you'll see that once we have HC, we can get the rest of the field quantities basically doing this. We can say the curl of H here will be equal to J omega epsilon times E, right here. And then we'll have the curl of E equal to minus J omega mu times H, and I'll just tell you about this. This is sort of an iterative process, but he lays it all out on, before we get to the TM case, he has a section there where he shows all the derivatives that are associated with EX, EY, EZ, HZ, and here's the deal with this one. There is no H field, there is no E field in the direction of propagation, right? Only an H field. Now when you take a look at curl of E, if you take a look at curl of E here, equal to the H field in the Z direction, the curl of E is going to have a derivative of EX with respect to Y, and it's going to be minus the derivative of EY with respect to X in the AZ direction equal to this. You can write these equations and basically go ahead and iteratively solve them. It's not hard to do, but it's kind of, if you want me to, I'll do them. They're intricate. What page are those equations on where he has all the derivatives laid out and how to get the answers? I've never really forced students to do these. They're just exercises and taking derivatives, to tell you the truth. Page 396. Let me just tell you how you do this. Page 396, all right? Well, if you take a look at this one, curl of H, right? Well, this is actually something that I prepare for, and it's going to be something that could be a little sloppy, but since we have EZ equal to 0 on this case, equal to 0, we can take derivative of HC with respect to X, derivative of HC with respect to Y, and then we can take the curl of HZ, set it equal to this. This would be, the curl of H, we're going to have two components. This is going to be kind of a lengthy one, but I'm just going to forego that and say that I'm not worried about those electric field equations. I would give them to you if you needed them. The real thing I'm going to tell you is this. After all is said and done, this is for the TE case, there's a couple things that come out of this that you need to contrast. This you write down. The velocity, phase velocity, beta, lambda in the guide length, are all the same for TE or TM modes. They're the same. Where the difference is the impedance. This would be like the characteristic impedance. I wish you could stop that. Anyway, the characteristic impedance for the TM mode is equal to, it's going to be eta as if it was unguided times the square root of 1 minus FC over F squared. The characteristic impedance of the TE mode is equal to eta unguided over the square root of 1 minus FC over F squared. Eta is equal to the square root of mu over epsilon for these modes, and this is lossless, by the way. Both of these are lossless. Okay, so this is a character, like Z naught for a waveguide, characteristic impedance, right? You'll notice one thing, for TE, the characteristic impedance is equal to or less than that of just material with mu and epsilon, right? Unguided. And here the TE is greater than, and the closer you get to the cutoff frequency, the greater the impedance gets for TE mode, all right? Now, one other thing about the TE mode that's important, since this HZ is the thing that really describes, that's the thing you need to get all the other field quantities. If you take a careful look at that, you'll notice something. I can have if you just look at this, I can have a TE10 mode, I can have a TE01 mode. And if you look at the cutoff frequencies associated with that, let me put it down. F cutoff is equal to really the speed of light over the square root of epsilon relative in the guide divided by I'll do it this way. When I give you the cutoff frequency, it's 1/2 square root of mu epsilon, and then it's equal to and that's equal to, I had written this down earlier, didn't I, class? Cutoff frequency is 1/2 square root of mu epsilon over this stuff, right? So these are the cutoff frequencies associated with the M and N mode, but I want to show you this. For the TE mode, this would be MN. When we have the TE mode here, I can't have M and N being 0, and here's why. If you look at this, if M is 0, this cosine just is 1 all the time, right? If N is 0, that cosine is 1. So only thing I have no variation with X or Y in terms of the E or the H field doesn't vary with X or Y, neither with the E field. I just have this, right? And that's a disallowed mode because M or N have to be 1, or I have no variation of the H field. And to be frank about it, if I have no variation with the H field, what you're going to see is that the E field itself is 0 in the guide completely. All right, there's a few other problems with that. So either M or N has to be 1. And usually the lowest frequency of operation for all the guides, write this down, and I'll put this. The lowest frequency is going to be, the cutoff frequency will be for the TE10 mode. And that cutoff frequency is 1/2 times the square root of mu epsilon, and then it's just 1/A, or over A. Because M would be 1, N would be 0, so it's 1/A. Now, what that actually means is this. If you just bear with me on this one. When you look at a waveguide, and you look at from 0 here to here, what it means is a half wavelength will just fit there. So this would be exactly λ/2 at cutoff. And that's the lowest order frequency. Does this make sense to you? It has to, the field has to be 0 here, has to be 0 here. At cutoff, it's just banging back and forth, right? Now, if you take a look at that for the TE10 mode, well, that means it's really would be 1/2A, and this would be really, I could say it's C over the square root of epsilon relative here. Now let me see if I can do this. Let's assume epsilon relative is equal to 1. So I have C/2A is equal to the frequency, cutoff frequency for the 1 ohm mode. And that means that A would be equal to C/2F sub C. And C/F is the wavelength divided by 2 would be exactly half a wavelength. You all see this, class? The way I always think about it is when I look at a waveguide, if I don't want to know what the cutoff frequency is, I look at the widest part of the guide. I take that and I set that's equal to half of a wavelength, whatever it is. Then I can get the full length by multiplying it by 2. And I know I have to propagate at frequencies higher than that. Now here's the trick with propagation. Dr. Wentworth's book will say to calculate all the modes of propagation up to like 3.5 gigahertz for certain dimensions. And you'll get the O1, the 1-1, I mean the O1, 1O mode, then you'll get the possibly the 2O, then the 1-1, and then the 2-1 mode, and you'll have a bunch of different possible modes up to there. You only want one mode propagating with the waveguide. So normally what they do is this, and let's do a problem like this right now, just so I can show you something you can get your teeth into and appreciate instead of a lot of abstract stuff. We'll do a few problems actually here before we move out of it. The impedance is the big difference on this one. Characteristic impedance. And it's really a ratio of EX to HY or EY to HX. Have you all seen waveguides class? Or not? You haven't seen them? After class, walk upstairs with me. I'll show you some typical waveguides, unless they clean them out of there. This is where the anechoic chamber is. They're just square pieces, they're long rectangular pipes. And I want to tell you one other thing about a waveguide that you should appreciate. You don't ever want to put,
Is a fiber optic cable a waveguide?
It is, but it's a dielectric waveguide. We're going to get to that. These are conducting waveguides. I want to just tell you one thing about waveguides. Now, they're used a lot for microwave energy, usually from about a gigahertz to about 40 to maybe even 80 gig. They use waveguide to communicate power, really. But you never want to take something like a hammer and hit them, because a small little dent in that surface will cause a very hot, localized hotspot and an impedance mismatch. Just remember that. They have to be constant cross-section. You can't have any kind of permutation, or else you get an impedance mismatch and it's bad. And it's not like, a little crimp on a piece of coax. This is a waveguide, so waves bounce into there and then bounce back hard. All right, now, to do a problem, so we actually get a feel for this, let me give you this one. Suppose I have the dimensions of 2.5 centimeters and call this right here 1 centimeter, right here, and fill it with air. This is our waveguide. And what I want to first to do is find out what the cutoff frequency is for the 1O mode, the cutoff frequency for the 2O mode, and the cutoff frequency for the O1 mode, then the cutoff frequency for the 1-1 mode. Now, the way this is shown is FC and it's M, N. So for the 1O mode, I had it down there already. If it's air filled, it would be C divided by 2A, right? I'll just put down what the cutoff frequency is. The cutoff frequency, in general, for the TE, or for any mode, for the MN mode, was equal to C, for this one, since it's air, C over 2 times, then it's the square root of M over A squared plus N over B squared. A is 2.5 centimeters, B is 1 centimeter. Remember, a centimeter is 10 to the minus 2 meters, right? Gotta make sure of this. So just tell me what the frequency is for the 1O mode on this one. C is 3 times 10 to the 8th. What do you get? This is what, 3 times 10 to the 8th? Over 2, and A is 2.5 times 10 to the minus 2. So that's going to be 3/5, right? 8 and 9, 10 times 10 to the 10th. That's what? 0.6 times 10 to the 10th, or 6 times 10 to the 9th gigahertz, right? Isn't that right, class? You have your calculators or not?
That's right.
Yes. 6
All right.
gigs.
6 gigahertz, right? What's the next cutoff frequency? What's the 2O mode? Well, it's going to be twice that, right? That just goes, M becomes 2 here, right? So it would be, this would be 12 gigahertz, wouldn't it? All right, now what's the O1 mode? Here, instead of taking C over 2A, it's going to be C over 2B, right? And B is 1 centimeter. What is that one going to be?
1.5.
Not 1.5. Think about it. Think about it. If this is 1 down here, right? What happens? I have 1.5 times 10 to the 10th, right? That's 15 gigahertz, isn't it? Sure. That's 15 gigahertz. And what's the 1-1 mode? Now you have to actually do this. If it's the 1-1 mode, it's 1 over A squared plus 1 over B squared, square root of it. That I can't do in my head. What'd you get, guys? Anybody? What'd you get? Come on, it's not that tough a calculation. What did you get? Did you get? I'm texting them.
Can you explain how you get the 1 again?
Yeah, all the M and N are associated with the mode numbers. Like I have F, C, M, comma, N. So a 1-0, M would be 1, N would be 0. 1, 0. Alright? That's the only thing I'm trying to show you. Got me on this, guys?
Yeah, that makes a lot of sense.
I'm sorry if I didn't say that clearly. Yeah, are you with me on this, Josh? Can you see it okay?
16
Yes, sir.
gigahertz.
What did you get?
16 gigahertz.
Is this 16, guys? I'm just making sure. It's in the right direction, it's higher. I just don't know if that's it. Anybody? Okay, 16 gigahertz. Now what I'm showing you is this. As these numbers increase, 1, 2, 0, 1, 1, you can see the frequency gets higher and higher, right? Now, when you would operate this guy, typically, if you look at it, the cutoff is 6 gigahertz, the next frequency occurs at 12, right? That's the next mode starts in at 12. So you would want to work between 6 and 12 gigahertz. Here's something typical. Usually this side and this side, the ratio is about 2 to 1 or 2.5 to 1. That's the reason I chose those dimensions. Almost always. The reason they have those dimensions is so that the next highest mode will be clearly separated. The low frequency is 6, the next mode comes in at 12. So operating that guy at 10 gigahertz is safe. Follow me? Or at 9.5 gigahertz, which is typically done. By the way, do you know what frequency 10 gigahertz is in the bands? Do you know your bands at all? You've heard of X band, K band, right? If you have a radar detector, K band's all over here because the police use it. X band is about roughly, it's about 8 to 12 gigahertz, but typically 10 gigahertz is X band. That's what most radars operate when they say X band, right around 10 gig. KA band is about 18 gigahertz. Then there's KA band is about 32 to 33 gigahertz in that range. That's what the police are using out there right now. And there's a KU that appears up north. If you drive up there, you'll have police with that. And then it'll be a regular K band around 18. But you'll see these band numbers. This started a long time ago, back in the days of UHF and VHF broadcasts, when the bands got designated with letters. And you have to know that L band is like really 1 to 2 gigahertz. Then there's S band. There's, I think it's 2 to 4. C band. And then they're going to have X band. They follow no logical order. I'm just telling you, this stuff sort of, somebody just threw this stuff together, and I don't know, maybe there was logic to it at one time, but it doesn't seem to be. So these bands have all different numbers, and they're associated with all different sizes of waveguide. Just remember that, the frequency of operation. So that's sort of it in a nutshell about the waveguide business for frequency. If I wanted to know here, if it's in the 1.0 mode, just listen to me. I'm going to show you a few more things. What would the characteristic impedance be? I want to know Z for the PE10 if it's operating at frequency of 10 gigahertz. Now this is a legitimate question that I could ask at a quiz. So what would that be? Let's assume it's airfield. what is the impedance? What is the intrinsic impedance of air or vacuum? 120 pi or 377 ohms. So this is 120 pi ohms, right? Now, what was the TE modes? Do you remember what the impedance was? It's going to be eta unguided divided by what?
Square root of 1 minus FC.
Right, 1 minus FC over F squared. Right? For that guide right there, that's 120 pi divided by the square root of 1 minus, my cutoff frequency was 6 gigahertz, right? I'm operating at 10, and I've got to square that. So what's the characteristic impedance? This is for TE. This is a very common thing that I'll ask.
So 471 ohms.
Is it 470? 471 ohms? Is that, anybody else second that?
Yeah.
All right, so it's greater than 377, right? Not by a whole lot, but by enough. Right? Well, what does that mean? Well, it means that if I have this piece of pipe, and I'm looking at it this way, what really is the E field ratio to the H field around there is 471 ohms. Follow me? So now if I want impedance matching, think of it as a coax cable. Then I want this thing feeding something that is going to have an impedance. See, this is something you haven't really delved into yet. It's going to be a little more complicated until I go through antennas. What they really do with these things is, if you have a waveguide, let me look at the cross section of this, like so. What they'll do is put a little hole here, and they'll put a short antenna down here. And that antenna will energize this guide, and the impedance of this antenna with respect to the grounded surfaces there will be Z0, will be the operating impedance of the waveguide. You follow me on this? Because it's exciting an electric field, and the electric field would be associated with the voltage between here and here, and a current, and the current would be literally flowing down the antenna or flowing on the surface there. That would be the same ratio as the impedance right there, the 471 ohms. Now, we haven't covered antennas, so I can't do that problem entirely because you don't know enough about antennas, but you know an antenna is just, at least one antenna type is just a short filament of wire. You all know that, class? And that's what excites these waveguides, and I'll show you. Now, we could get into this. This doesn't have to be a half wavelength long or anything. We'll get to that later. But that's how these guides are exciting. And literally, the way they pull off energy, too, can be like that. A lot of times what they'll have is this. They'll have the waveguide, if you look at the square thing right there. And what will go on to this, they'll have this thing just flare into a horn antenna. And we have to cover antennas before I can do this, do the impedance on that one. But the impedance will be matched so that nothing will be reflected. That's the goal of this. Okay? All right. I could do one other thing too. This is a question I could ask. For this mode of operation, 10 gigahertz, right? Next thing I'm going to ask, what is the velocity of energy down the guide? I want to know how fast it's moving. How do you do that? Not phase, but energy. What do you do? Let's look at their notes now. Which is good, because this stuff's a little dry unless you see a problem.
The speed of light over the square root of epsilon relative.
That's phase, isn't it? Not energy. Energy is always less than speed of light, right? Energy would be what? C times the square root of 1 minus FC over F squared, right? Phase is C over that. Y'all remember that? I'm asking for the velocity of energy, not the phase velocity. Didn't I put that down on the board, class?
Yeah, you wrote it as C over square root of epsilon relative.
It was C squared over epsilon relative, C squared over epsilon relative times.
Divided by
Divided by
phase velocity,
phase.
right? But it comes out to, when you divide by the phase velocity, you have C times this. And I put phase times energy velocity is speed of light squared in the media, right?
Is it C times that square root, or is it C over the square root of
C
this?
over the square root of that would be the phase velocity. C times it is the energy velocity. Energy is always propagating less than speed of light. Phase is faster than speed of light. Maybe phase is fictitious. That's the thing. Does everybody have that, class? if I didn't state it clear enough, realize this. Phase velocity will always be c over the square root of epsilon relative divided by square root of 1 minus fc over f squared. That's phase.
Yeah.
Energy will always be c over the square root of epsilon relative divided, or times the square root of 1 minus fc over f squared. So that's, say that again, what is the energy, speed of energy down there? Just tell me what 1 minus the square root of fc over f squared is. Tell me what that is. That's what? 0.6 squared is 0.36, right? 0.36 from 1.
0.8.
Is it 0.8 the square root of that?
Yes, sir.
So this is 0.8. So it's 80% of the speed of light. With me? I'm sorry if I didn't say that as clearly as I should. Y'all see this, class? And that's important. One last thing, what's the wavelength down the guide? What is lambda on the guide? Pardon?
Whatever the speed is.
Now you don't use the speed, you use what? Phase velocity, don't you?
Phase velocity.
And really it's going to be this. Listen to me. It's the wavelength in an unguided medium. Think of that. That's C over F for us, right?
Yeah.
And then divided by that square root of 1 minus FC over F squared. The wavelength lengthens. It goes to infinity at cutoff.
Yeah.
And what do you get for that? So it's 80%, and you're going to be 1 over the wavelength and unbounded wavelength, wavelength and unbounded guide divided by 0.8. And that's C over F, so 3 times 10 to the 8th over 10 to the 10th. And that's 3 centimeters. 3 centimeters divided by 0.8, whatever that is.
So 3.8 centimeters.
Is that right? Anybody? Okay. I'm sure there's a use for that. One of the reasons I'm saying that is because if you have periodic localized hotspots, they'll be periodic in about every half wavelength. And I'm going to just tell you, that's something for another day. You probably deal with this more in the microwave class than here. Got me on this? So this is sort of, the nuts and bolts of waveguides is this, rectangular waveguides. You can have conducting rectangular waveguides. You can have a TE or TM mode. Almost all the time it's the TE mode. Almost all the time it's the 1O mode that's used. Now there are exceptions when you're going to be doing certain things where you have splitters and stuff like that, but that's fundamental. For now, it's good enough for you guys. The bottom line is when you have a waveguide, you want to make sure you operate it between the TO 1O mode and the next normal mode, which is usually the 2O mode. There's 1O, 2O. And you operate it about halfway between. So if it goes between 6 and say 12, you operate somewhere around, well, you can operate 8 to 10. Higher up is better. The further away from that lower cutoff, the better it is. So around 10 gigahertz. And that is an X-band guide, by the way. All right, waveguide. Now, after this, now we're going to get into something, and I'll let you do some more problems, dielectric waveguides. Now, first, before we get into fiber optics that you mentioned, dielectric slabs guide waves too. Matter of fact, anything where there's an impedance discontinuity tends to electromagnetic energy hugs it. I mean, I'll try to just tell you that all sorts of phenomena, but even if you have just a slab of metal and you have an electromagnetic wave coming, there's something called a surface wave. That energy, a lot of it at least, hugs that surface. It just kind of attaches itself to that surface, and there's a lot of reasons for it. But this is a dielectric slab waveguide, the next one. A dielectric slab. So let me show you what it looks like. These are used, by the way. A dielectric slab is nothing more than a piece of dielectric that has some epsilon relative. This has some dimension A, and well, Whitworth's book actually calls this dimension B, and this dimension A. Here, A is much less than B. Remember that. A is much less than B. And this is just a piece of dielectric. There's no conducting surface. Now, what happens in this thing is that the electric field's direction of propagation bounces down there. If we were to look at this guide, what we'd see is this. Let me build this a little higher, and I'll show you. If this is the cross-section of this slab right here, so I'm looking down the slab like it was coming out of the board, and I'm looking this way. So this would be dimension A, but I blew it up. What's happening here is this. There's an electromagnetic field, and I'm just going to show it like this. Doesn't matter the direction. I mean, it doesn't matter if it's T or TM at this point. It's going to come in, slam into that surface, then it's going to come down, hit this surface. At this surface, there's a reflection coefficient, call it tau right here. I mean gamma, right here. At this surface, there's a reflection coefficient. And it's just going to bounce its merry way around here. Now follow me on this. So Dr. Whitworth says that he's going to assume the field just before it hits there, that's the incident field. He calls it EA, and he says let EA be equal to some E naught. And he didn't say if it's TE or TM. He didn't say if the field's sticking out, that would be TE, or if it's in the plane of the board. For our purposes, it doesn't matter yet. The wave's direction does, and it comes in on an angle theta incident. Just write this down. It reflects off, here's the reflection, at an angle theta incident as well. I think y'all can imagine that, all right? Now keep watching. It hits here, and then it comes off, and this angle would be 2 theta incident. That should make sense to you because if you split this up the middle, this would be theta incident on that side, theta incident on that side. Now here's the point you have to pay attention to. And if somebody tells me where this is in this book, it would help, but what he's going to say is this. What page is this on his book? His Dielectric Guides, he's going to have a picture.
Page 400.
400.
It's like 400.
That's the one I want. What page is that?
400.
Page 400. If you look at page 400, try to appreciate this. Now what's happening is, just listen now. Electric field comes in here, hits here, there's a reflection coefficient, right? It's going to multiply this value. Then this thing is going to propagate down here and smash into this surface. You have to multiply it by the reflection coefficient again, right? So I got gamma squared times the incident field. Then it's coming back up here. And he labels this point A, he labels this point B, and this point C, I think, in his book. Now, what he does here is he says, at this point, he's saying this is a constant phase surface and it's propagating this way. Now, this is constructive interference at that point. It means when you take this wave and you bounce it one time like this and hits here, they have to be in phase. They have to have the same phase and same the same phase for sure. The magnitudes can be slightly different. All right? Now, the other thing is, this guide has to operate at an angle such that this angle is equal to or greater than the critical angle. Remember, the critical angle is what? The angle where everything bounces back. Do you all remember that, class? Everything bounces back. There's no transmitted power. So nothing goes in that direction, basically. So here's how we go about this. I guess first I should do the critical angle. I'm trying to get this in today, but I don't know if I will. If we wanted the critical angle, and we'll call this region 2 and call this region 1. This is air outside there. And this would be some epsilon relative to. Then the critical angle we would have eta 1 times sine of theta incident would be equal to eta 2 times sine of theta transmitted, or actually, let me do it this way. Not out of time, but we'll say this region has some epsilon relative. It's not, call it epsilon a relative of dielectric. Here, epsilon relative is 1 for air. So I can say the square root of epsilon relative dielectric here times the sine of the incident angle right there has to be equal to the square root of epsilon relative of the air, which is 1, times the sine of theta transmitted. Now here's the deal. Theta transmitted is going to be 90 degrees for the critical angle. So if it's theta transmitted is 90 degrees, the sine is 1. So that means 1 over the square root of epsilon relative 1 is equal to the sine of theta incident, or the sine minus 1 of this is the incident angle, such that the incident angle, I'll call it critical. The incident angle has to be greater than or equal to the critical angle for anything to propagate, keep bouncing back and forth and not transmitting, okay? That means I can't have a mode where I slam it straight up and down, because what will happen is some of that's going to be transmitted and the thing will die down. But if you're at that angle or higher, then everything bounces in between that waveguide. Everybody understand that? Now the way we get the modes is this, and this isn't something you're going to like, but we have to say that there's an assumed wavefront, that these waves are banging this way and that way. And there has to be coherency, or this one bouncing down here, coming up to that wavefront here has to be the same phase. So what they do is they'll say, well, I'm going to have EA here, then I'm going to have I'll call it E0. E0 times gamma is right here, and gamma is going to have magnitude gamma e to the j phase angle associated with gamma. Then it's going to be e to the minus j beta, and it's going to be this length. So that's C to B. Wait a second. No, A. That's A to B. Times L A to B. And then it comes down here and hits, so it's gamma again, so it becomes gamma squared, and then there's a 2 here, because now I'm going to have 2 of the phase angles. And then it's going to be e to the minus j beta and L B C here. And when you look at that thing right there, it says that all these phases right here have to be equal to either 0 or 2 pi or 4 pi or such. So the way they write it, Dr. Wentworth's book, he has beta times LAB plus LBC minus 2 times the phase angle here has to be 2 pi m. Now what m is a weight, it has to do with the mode number. And as m gets larger and larger, this angle gets steeper and steeper, closer to the propagation right down the guide. Do you follow me on this, class? Please just understand I'm trying to do my best and I'm about out of time. I'll finish this next time. But LAB and LBC can be rendered in terms of the angle, cosine of the angle, and the actual spacing distance. And I'll get it next time. I'm sorry, I ran out of time. Now, I said there we didn't have enough stuff for the quiz. We frankly, last time you had plane waves, on chapter 6 we did a quiz on that, right? Why don't we hold off the quiz till Friday, all right? And I won't give you one Wednesday, I'm going to give you some homework. I want to finish this up because waveguides, the essence of waveguides I haven't really, can't really get at everything until I get done with that class, but at least got to bring you up to speed with dielectric waveguides.